sorry I couldn't make it yesterday, but at least I'm here now. So since we are running out of time, I will straight away come to the topic, and my previous two speakers have actually discussed most of the things that I wanted to talk about, so they have made my job easier. So before I proceed, first I would like to acknowledge the students and staff and the sponsors. Mr. Dr. NP is one of the faculty in IIT Bundelkhand, and Dr. Karmakar, after doing his MTech with me, he went to Dr. Acharya for his PhD. He has just finished and hopefully is coming back. And other MTech students, and then the project staff and sponsors. So this is the presentation overview. I'll talk a little bit about the background and justification, and then that brings out the objective of the present presentation in the experimental details. The setup in this experiment is pretty critical, so I'd like to devote some time on that. Then the measurements, then the results. Results are divided into two categories. One is the dynamics and stabilization, and I will come to that, what I mean by that, when I come to the background and justification, and then the conclusion. Now, thermoacoustic oscillations in combustion systems are well documented and studied, and we have devoted many sessions in various workshops on combustion instability, thermoacoustic instability. However, low frequency oscillations have also been reported. For example, my previous presenter just talked about the precursor to blow off, the vortex shedding, which are low frequency oscillations. Similarly, flame flickering, which Dom was talking about, that is also a low frequency oscillation. And also in some practical combustion system like gas turbines, hooting has been reported, which are about 150-160 Hz. Doesn't correlate with any acoustic mode. So these frequencies is what I'm going to focus on. They don't directly correlate with the thermoacoustic oscillations. They correlate mostly to the hydrodynamic oscillations, and that is what I'm going to focus on this. So these are usually reported in presence of vortices or recirculating flows, as Pat has just pointed out. So essentially hydrodynamic or fluidic oscillations. And also there has been report of mode switches, where it switches from one mode to another mode. So I'm going to discuss this also. So when we have, first of all, what are the consequences of this? When we have low frequency, we have longer wavelengths. So typically they are responsible for flame out, just has been pointed out by my previous speaker, because the stretching is going to be more, and lower ranges of audible frequency are more annoying. This is something coming from the practical user's point of view. When you have an oscillation of about less than 200 Hz, they are much more annoying than high frequency oscillations. So, and these oscillations are governed typically by the velocity field fluctuations. So essentially convective time scales are more important. Yeah, so convective time scales are more important. So needs investigation to better understand the flame stability and to improve stability limits, particularly pertaining to these low frequency oscillations which are convective in nature. And one of the practical applications which is emerging very rapidly is the lean blowout combustors. So the objective of the present work is first of all to develop a combustor dominated by these convective modes. That's why I said that the experimental setup is critical here. And then to understand the combustion dynamics for such a combustor, which is the coupling between pressure, heat release and velocity fluctuations. And then we'll talk about the reduction in oscillation by passive stabilization. Here I'd like to point out that my previous speakers talked about vortex shading, reducing the stability limits. But what I'm going to show is improving stability by vortex shading. Okay, the other way essentially, which is very routinely done in combustion oscillation control. Something which is not beneficial in one case is beneficial for other case. So the experimental detail, I will talk about the development of the combustor, then measurement and data reduction. Now here the data reduction is also very critical, because what you will see is that what Dom has pointed out, that we do a intelligent filtering to get the frequencies that we are looking for. But here we have not done anything like that. We looked at the full spectrum and tried to identify different modes from there. So therefore data reduction plays a very important role in the analysis. So here is the combustor. This is a standard dump combustor. This is a schematic of the flow field in a dump combustor, which has been reported by Forrester and Evans in 1997, and there has been a lot of study done on this combustor, where the flow comes here in the dump plane. We have a recirculation here, then it reattaches somewhere inside, and then the flow field, the fully developed flow field, goes out. So typically, if the length of this reattachment length has been reported to be about 8.2 times the dump height. So if you have that, we get a fully developed flow. There is no specific recirculation coming here. What we wanted to do is, we wanted to have a recirculation coming back from the exit. so that we get a stabilization inside the combustor. So we'll have two modes of combustion stabilization. One, the flame anchored here, other is aerodynamic stabilization because of the recirculation coming back from here. So we chose the aspect ratio less than this reattachment length. So for our combustor, which is schematically shown here, the length of the combustor was 7.5 times the dump plane length height, which is less than 8.2, which is the reported reattachment length. So there was a reversal of the flow from the exit plane. As we can see here, a recirculating vortex is created here. This is a typical flow visualization. And then we have done some analysis of the getting the streamlines and all, and we see a recirculating flow is not very clearly visible. We get negative values of the stream function, shows a recirculating flow at the exit. Then these are the velocity field. This is the turbulence kinetic energy. Because of this recirculation, you can see that at this point here, there is an increase in turbulence kinetic energy, which is much more compared to what we get in the potential probe, as well as the turbulence dissipation rate is also much higher. So this zone, which is somewhere about here in the combustor, is where the flame is expected to stabilize if it blows off from here. So we get aerodynamic stability primarily because of this recirculation. And then what happens is that when the flame is burning here, we'll have different convective modes. One mode will be the supply of the unburnt reactants to this flame, and then recirculation of the burnt products from the exit. So we have multiple modes taking part and in the dynamics of the combustion. So different measurements have been carried out. We have measured the pressure fluctuations at different locations. This is the schematic. We have two screens. One screen is the main flashback arrestor, and then another screen to provide some kind of flame anchoring. And then this is the combustor, which is optical axis was provided here. We did CH chemiluminescence, and I'd like to point out here that we have depended heavily on the paper by Dom on the chemiluminescence, and even the Rayleigh index we are going to talk about. We have taken the definition from his work. So this is the entire measure. So we have done flow visualization, pressure measurement using piezoelectric water fluid pressure sensors, then heat release measurement using CH chemiluminescence, and we have not calibrated it, and the flow rates were measured using calibrated rotameters. Now the data reduction, as I said, is very important. If I look at the pressure and heat release FFT plots, we see that the pressure and heat release peaks don't coincide. Okay, this is first thing that is, if we look at thermoacoustic oscillations, typically pressure and heat release frequencies match with each other, but not in this case. As you can see, and there are multiple modes, as I said, are available in the pressure oscillation. Similarly at heat release oscillations. So first stumbling block for us was to define the phase angle or define the frequency of oscillations. So what we did was we defined a new parameters which we called most correlated frequency. For that what we did is we did a cross correlation of the heat release and pressure oscillation in the frequency domain itself, and look at the correlation coefficient, and then the maximum peak that we got here we defined as the most correlated frequency. So this is the frequency of most correlation between the pressure and heat release oscillations, defined like this. Then the Rayleigh index was defined as defined by Dom in his paper, as P prime Q prime dt integrated over time and then normalized by the total time. And the phase angle, again for each and every frequency we have got the phase angle like this, because as has been pointed out, phase angle basically scatters all around the place. And since in this particular case we don't have a well-defined frequency correlation, first we looked at the phase angle variation for all the frequencies, then we just identified the phase angle corresponding to the most correlated frequency. For this practical case, I think it is a Reynolds number of 5302 and equivalence ratio of 0.8, it came out to be about 310 degrees, which is in the third quadrant, in the fourth quadrant, the driving zone. Now, with this background, let's come to the results. I talk about the visualization, then dynamics and stabilization. Our operating conditions were air flow rate range from 50 to 100 LPM, which corresponds to a Reynolds number of 2791 to 8189. However, these two limits are, this was less than the flashback limit, this was more than the blow-off limit, so these are not reported, although we did the velocity field analysis for that. The fuel flow rate was changed between 3 to 7.5 LPM, that ranges the equivalence ratio for a practical case from about 0.6 to about 1.1. The first look at the flame visualization. This was at different Reynolds number when the fuel flow rate was 3.5 gram per second. So the equivalence ratio corresponding to 5302 was 5023 was 0.8. This is at a lower Reynolds number. The flame was anchored at the first screen. When we increase it, it still remains anchored, but the flame height increased. Now when we go to a higher Reynolds number, blow off occurs from here. Flame is no longer anchored. So we have got a blow off condition, but because of the geometry of the combustor, because of the flow reversal from the exit section, the flow remains still stabilized because we have a aerodynamic stabilization here. Now this switch is what we wanted to look at. Right? The thing, that phenomena is still we have blow off, but still we have not lost everything. We can still continue to take measurements. So that was the beauty of this combustor. And then we continue to increase the Reynolds number. The flow still remains, but essentially as you can see that the flame front is moving away because of the Reynolds number is increasing. And beyond 6140, if we go beyond that, the total blow off occurred. Now these are the flame images with time for this case 5032. You can see some kind of flickering occurring at with time also at 6140. So now coming to the dynamics of this. This is the plot of Reynolds number for say RMS pressure in dB for all these conditions. We can see that till the flow was anchored to the tip, the oscillations were quite low. It was less than 94 dB. And then when the first blow off occurred from the anchoring to the aerodynamic stabilization, we see a sharp jump in the pressure oscillations, going from 94 dB to 99, almost 5 dB increase in the pressure oscillations. So immediately the thing will come into our mind looking from the classical combustion instability that the instability has increased. But is that the case? If I look at the other parameters, for example the frequency initially, once again the heat release frequency was pretty low, pressure frequency was moderate at about 70 to 80 Hertz, which corresponds to the overall incoming pipe length, okay, and the convective scales. Then it was, first of all, as I said, this is not thermoacoustic because as we can see that as we increase the Reynolds number, the frequency is decreasing, which acoustically should not happen because it will not be depending on the Reynolds number. So here the frequency is slightly decreasing. When we come to this point, another interesting this when this jump occurred, initially as we can see that the most correlated frequency was essentially the heat release frequency. So this was heat release driven oscillations. Suddenly the most correlated frequency is the pressure oscillation, corresponding to the pressure oscillations. Therefore now there is a mode switch. Initially it was heat release driven, now it is pressure driven oscillations. And then is a very low frequency oscillations continued, less than 10 Hertz, and then finally it blows off at beyond this point. At this point now all the frequencies are same. Heat release oscillations, pressure oscillation, most correlated frequency, everything converge, and then finally the blow off occurs. Now the phase angle, if I look at, again shows a jump. This was the anchored flame. Initially it was increasing, so we are moving towards more instability. Suddenly when the jump occurs, there is a drop in phase angle. Now it goes into that, here it is a rising zone, more than 270. Suddenly it has come down to the damping zone. So the flame has become more stable when this increase in the oscillations occurred. Flame has become suddenly more stable here because it has gone from the anchoring to the aerodynamic stabilization, and then again it monotonically increases. Now this becomes more clearer in the plot of Rayleigh index. We see that when the flame is anchoring, it was almost neutrally stable, and Rayleigh index is almost 0, slightly unstable in this point. Then when this jump occurred, it has become negative. So flame stability has improved, or the instability has reduced, let me put it this way, from Rayleigh's criteria. And then beyond that point we have a gradual increase in the instability. So when we have a lifted flame, usually for these two conditions, the lifted flame is more unstable than the anchored flame. Only when the switch occurred, there is a improvement in the stability. So this points to two things. First of all, we cannot just say that when the pressure increases we have more instability, because pressure changes can occur because of various reasons. For example, here what happened is the location of maximum heat release changed, and it became very close to the location of the pressure measurement. And then where the heat release oscillations were bringing in the changes, we get much more changes in the pressure oscillation, even though the flame is more stable as has been shown from these 2 points. The sound pressure level has increased, but the flame has become more stable. So this is not violating Rayleigh's criteria at all. Actually, it is confirming that Rayleigh criteria is applicable to combustion process with thermofluidic instabilities. Now, continuing with the lifted flame, we are looking at this flame here. The flame dynamics at Reynolds number 5032. As we can, if I plot the FFT of the heat release and pressure oscillation, we can see that the heat release again is a multimode, pressure is also multimode, but this pressure, this second peak of the pressure is the harmonic of the first peak. So essentially we can consider only one mode. Like to point out here, this is the full spectrum of the pressure oscillation. We can see that about 17 Hz is by far the most dominant. The next is its first harmonic, and then the other acoustic modes and all are almost non-existent. Actually, is non-existent. No other mode is present here. So, because of the fact, because of this, we can say that what we are exciting is not acoustic mode. We are looking at convective mode, just to ensure that yes, we are indeed looking at convective mode. First of all, this is the most correlated frequency plot, the normalized P prime Q prime. We can see that the most correlated frequency now is this one, the second heat release peak. Okay, which is 17 Hz, which is not an acoustic mode at all, order of magnitude less than the frequency of first longitudinal mode, and the higher fluctuation that we have seen in the previous plot on the previous slide is because of the higher heat release rate here, because our pressure sensor just monitoring the pressure was located here. So because of this fluctuation we get higher pressure. So essentially it's because of the exothermicity. We reduces the density and decreases the pressure or changes the pressure. Now is a time scale analysis. This is just a cartoon of the combustor. Here is our main flow coming. At the dump plane we are going to have a deceleration because of the area increase. So it will be a function of this area ratio. But the flame is anchored here, so there is some heat transfer to this. So because of that it gets heated up, the temperature increases. So there is going to be an expansion. If I do an order of magnitude analysis of the convective time for this flow reaching this zone, which is unburned, reaching the burn zone, it comes out to be about 0.35 second, which is 2.8 Hz. That is exactly the frequency, almost as this 2.5 Hz we have seen here. So the first modes that we are seeing here essentially is coming from this convection of the unburned incoming product to the flame zone. Now looking at the second one, what happens is that now the burned products will move towards the exit, it gets reflected back from this exit section and come back to this. When that happens, it changes the local equivalence ratio and that will have its own convective time scale. So again, because of the combustion, the temperature is going to increase almost tenfold. So because of that, there is a massive acceleration of the gases, so the time scale is going to reduce. So when I did the calculation of the time scale from the flow going from here to here and then coming back, which comes out to be about 0.06 seconds, roughly about 16.7 Hz. That is the frequency that we have of the flow reversal coming back to the flame zone, and that matches with the second mode of the heat release oscillations that we have seen, that is shown here. So therefore, and now this is our most dominating phenomena because that is the most correlating frequency. So we can say that the dynamics is governed primarily by the flow reversal from the exit section, which is the fluidic oscillation that we have just discussed. The next let's look at the effect of equivalence ratio. So once again we kept the Reynolds number same and we varied the equivalence ratio. This was the point that we have discussed so far. If we change the equivalence ratio on both sides, once again if we had a higher equivalence ratio or more fuel flow rate, this was anchored, the flame was anchored. Then it jumped here between these two. At a high equivalence ratio it was anchored, it jumped here, and then we have a gradual decrease like has been reported all around the literature that the pressure oscillation is going to decrease as we are reducing the equivalence ratio because the temperature is decreasing. Now once again in all these plots, whenever there is a jump, we are seeing that corresponding to jump we have an increased stability with respect to equivalence ratio also. Previously we showed with respect to the Reynolds number, with respect to the equivalence ratio also, when we look at the flame going from anchored mode to the aerodynamic stable mode, the stability improves, the stability is increasing. And once again for all of them, the dominant mode of pressure oscillation is the most dominating frequency, that is shown here. So therefore, first of all, increased stability at lower equivalence ratio, which is quite obvious. The lower PA at lower equivalence ratio because the temperature reduces. There is an increased correlation between P prime and Q prime, as we can see here. The most dominated frequency is becoming equal to the pressure oscillation, and then that brings about an increase in the Rayleigh index. Now, just to continue with the same discussion, we took the same case where the flow was aerodynamically stabilized, 5032. This was the flame oscillation. We just inserted a small rod, which is about 6 mm rod, slightly away from the flame. And immediately the flame gets anchored again back to the tip of the burner. Now if I look at the pressure oscillation, without the rod, this was my pressure oscillation, this was the flame location. As we can see, there is a dip in pressure here because of the exothermicity. But when the rod was inserted, this dip was removed and we have a gradual increase very similar to the pressure rise that we see in any dump combustor. And then there is a drop because of the final expansion that is occurring from the exit section. Now the Reynolds number corresponding to this rod was 740. And this rod, as we can see clearly, has reduced the flickering. The dip in mean pressure I have just explained, and the flame is now anchored to the rim of the burner. What happens is that because of this strength of this rod, there will be a small stagnation region just ahead of this rod, and that provides the stability close because it is pretty close to the burner tip. So it gets stabilized at that point, and then the flame goes back to the tip of the burner and stabilizes there. Now, one thing that occurred to us that this improving stability, and we will see the dynamics also, is because of the vortex shading from this rod, because we have flow energized and there is more pressure recovery from this rod. So in order to look at that, first of all there is the pressure control dynamics. Without the rod, this is the oscillation, the peak to peak oscillation was close to about 1800 Pascal. With the insertion of rod, that comes down to about 600 Pascal, or 900 Pascal. So there is a 4 dB reduction in pressure oscillation when this slender rod was introduced. There is reduced correlation between P prime and Q prime, that is shown here. This was the heat release oscillation without the rod and pressure oscillation without the rod. When the rod was introduced, the heat release oscillations came down like this, and the pressure oscillations came down to a different frequency altogether, 55 Hz, which does not match with any of the frequencies that we have seen here. Now the question arises that where is this 55 Hz coming from? So for that, we went back to the classic paper by Williamson on vortex shading from slender rods, and he has reported that corresponding to the Reynolds number that we have, the Stahel number corresponds to about 0.182, and this is exactly, we have got about 0.18. So that is the frequency that we are getting corresponds to this 55 Hz oscillation that we have seen in the pressure. So therefore we can say that the oscillations in the pressure that we are seeing is actually because of the vortex shading from the stabilizing rod, which improves the stability here. And then this is the normalized or the most correlated frequency plot. We can see here that without the rod, the most correlated frequency was about 17 Hz, which we have just shown earlier. With the rod, it comes down to about 55 Hz, and still this frequency is much less than this frequency which we are seeing here. Rather, magnitude is much less than the frequency that we are seeing here. And another point I'd like to point out here is look at the correlation. This one corresponds to this scale, and this dotted line corresponds to this scale. There is an order of magnitude decrease in the correlation coefficient. So clearly now when we inserted the rod, the pressure and heat release oscillations are much less correlated compared to what they were before. So once again that points out to the fact that the correlation between pressure and heat release is primary driver of the instability that we are seeing. Looking at the phase angle, initially it was 310 degree for that condition. When we inserted that rod corresponding to the most correlated frequency, which was 55 Hz, it comes down to about 155 degree. So again there is a mode switch going from the fourth quadrant to second quadrant. So once again there is a mode switch where the phase shifts from essentially going from one quadrant to another quadrant whatsoever altogether. So the dominating driver is changing from pressure to heat release. And once again, since the phase angle is in the damping zone now, as we can see here, therefore the oscillations have gone down. So once again it is satisfying the Rayleigh's criteria. Now this plot actually has data from some other tests also I have not talked about. It's just a kind of summary of what we have done. This case is without the thriller, that is this one. We see that the stability limits with respect to the flow. This is the stability equivalence ratio, the blow-off equivalence ratio with respect to the Reynolds number, and the blow-off limits are given here. This is for this case. Then This is without a screen. When we put a screen, this is the one that is shown here. With a stabilizing rod is this one. So as we can see here, with the stabilizing rod, the blow-off equivalence ratio has come down drastically to about less than 0.6, and it is almost invariant with respect to the Reynolds number. It is becoming primarily dominant on the Reynolds number. But when we go to rather equivalence ratio, but when we go to the other test conditions like with different swirlers and all, then once again they go up. So essentially what this plot shows is that the blow-off limit is a function of equivalence ratio, no doubt, but it's as my previous speaker pointed out, it depends on the system problem, system level phenomena. So it depends on the Reynolds number as well as the geometry. So all of them come into picture when we talk about the blow-off limit as well as the stability of the flame. So once again I have to re-emphasize what the statement that he made, that it will be very dangerous to jump into conclusion by looking at a particular geometry and particular operating condition regarding the stability limits, because they are all interlinked. So and another point here is that, and coming to the conclusion, I have mentioned that the convective modes dominate close to the blow-off, which was also shown that the vortex shading and all have been shown by a previous speaker, is also shown by a previous speaker. In the particular case that we are talking about, flow reversal dictates the dynamic of the lifted flame, and this is typically the kind of flame we get in gas turbine combustors. So therefore, this flow reversal plays a dominant effect. So it is essentially a thermofluidic oscillation. There is a mode switch at the lift off, as we have shown. When the flame goes from the anchored mode to the aerodynamically stable mode, there is a mode switch. The stability improves just after the lift off, but the pressure fluctuation increase. Therefore, increase in sound pressure level is not a sufficient condition for increasing instability. The vortex shading affect the dynamic. A passive controller can be used to improve stability and blow-off limit. And the crux of the entire presentation is Rayleigh criteria is still satisfied, although Rayleigh did it for acoustic oscillation. But here in thermofluidic oscillation also, Rayleigh's criteria is satisfied in all the test cases that we have seen so far. So for more details, you can look at these papers, and some more papers will be coming soon. Thank you.